Like it attracts retards to it, like a trap.
I did music off.
It looks good, but it's a trap, honeypot.
Damn.
Yeah, like torrenting it.
You should use. You should.
Some torrents are honeypots where they'll catch your IP and tell your ISP to put on the internet. I know it's dumb. It happens to most of the movies.
Why don't you do it? Bootlegger like the same movie.
I can't do Spotify.
I don't do
it eats your data. Like if you're not on Wi-Fi, it'll eat.
All of my songs are downloaded.
Really?
To my house.
Yeah, you can download them. And like, but to download them, don't you have to like you have a subscription to it?
Oh yeah, but you can do too.
But if they send you the notice,
I'm like, oh, I don't even have Netflix. I'd like to steal Netflix and say, I use Spotify sometimes to stream. Like, of course, before I if I buy something, I want to make sure it's like I really like it. I'll buy it.
I don't buy it.
You haven't bought shit. Don't lie. I've never bought anything.
I have over 2 terabytes of torrented data on my computer right now.
Going to jail.
Apologized. I had some printer issues on my way here. Anyway, I also want to apologize. My intent was to have all the exams uploaded by yesterday, but I spent a good portion of the day yesterday at the doctor's office with my daughter, so
Are you grading the exams?
yeah, it turns out it turns out I'm grading all of it, yes.
Oh no.
Damn.
So, so that's, I spent a few hours on regrading.
Did the grader grade half of them, and then you're like,
Yeah, I
whoa.
was gonna have the grader grade a few problems, 2 of the problems, and
She's got rough hands.
it didn't work.
Whatever it is.
So
Yeah.
I've taken some time and,
Take your time.
Hopefully, I hope you bear with me, but I felt like I needed to give you back some points. So I'm almost done, and I'm not going to comment too much. I do want to go over the exams because there were a few things that I saw sort of that I want to address, and yeah. So, but I think I'm going to wait till Thursday. Okay, I need to try to schedule another exam if possible. So.
Another exam?
Mhm.
What?
Oh, you mean somebody else's
And
exam?
some-
Okay,
right,
I was like,
right.
we're gonna have 3 exams?
No. That has nothing. So I can't talk too much.
Okay.
I have to check. I think there's only one person that hasn't taken the exam yet. So, but I want to see if that's even going to happen. Okay, so we'll see. But that's why I don't want to comment too much on it today.
We have a quiz or homework Thursday.
There's no quiz or homework this Thursday. No, we're not going to have time to go over enough for us to have anything this week. So, and I think next week you're gonna see what material we're covering. So I think I'm gonna make that a turn-in homework rather than a quiz. The material is. It's fine if you have a computer and calculator. You can do a lot. Otherwise, it's the guess. We're ending up with equations that we can't solve numerically very easily. So we've covered chapter 4 up to flow of vapor. So we've done all the liquids. Right? We did all the liquids, flashing liquids. And now we're going to look at vapors and how it changes. So same thing, we're going to start with flow of gases through a hole. What we're not going to have here is we're not going to have a tank ever, right? Because we're not going to have the liquid height to worry about. So in that sense, it's simpler, but I'm sure as you can guess, it's a little bit more complex with a compressible fluid. Right? So a lot of times, because we have a gas, we don't have to worry about the delta Z term. There really isn't much of a, right? That's any change in kinetic potential energy is going to be negligible compared to everything else that we're looking okay, just because we're dealing with a gas. Okay, so we're gonna, we have the same, obviously, material and energy balance to deal with, but, right, what we have now is a density that's very dependent on the pressure, right? We're dealing with gases now, so as you know, the higher the pressure, the higher the density. Okay, but we're not gonna need to worry about this term, right? And we're really not gonna deal with shaft work or anything in this part of the course. But we do have one more thing, and that is when our fluid that's compressed in a gas tank, right? Usually at a very high pressure, when it expands through the wall, it will reach a maximum velocity past which it cannot accelerate. Okay, so what does that mean? That means that the pressure can't decrease past that pressure either. So, does anyone know what that velocity is throughout here? Past which it can't accelerate? It's dependent on, right, the movement in that medium.
Speed of sound.
It cannot exceed past the sonic velocity. So we're limited by the speed of sound.
Can you explain a little bit
What?
why?
So, yeah, I've actually gone back and asked professors who are teaching fluids and right. So I don't know that we want the full physics behind it because it's limited by how fast, right, sound waves can travel through a medium. If we just look at, so if we look at the hole in the, so this is just the tank wall, okay, so this is where we have a pressure, P naught. Now this is P naught now, this is absolute. We are no longer working in gauge pressure, okay? That is the one thing that you need to keep separated, right? That when you deal with this, you're often, so this is the tank wall. Okay, so it goes around the Newhandler, okay? So inside of here, you're often given that P naught, or the pressure inside the tank is whatever, 2200 PSI gauge. Okay, when we're dealing with gases, you're gonna have to add the atmospheric pressure to that. Okay, so if it's 2200, if it's 150 PSI gauge, then you're actually dealing with 164.7 PSI. And that's the number we need to look at. But if we look at if you look at the velocity, for example, starting in here where there's nothing, it's going to increase until it reaches sonic velocity. And we're going to call that choke pressure, choked velocity, okay? It's choked because it's basically what we're doing. We're choking the flow. It cannot increase past that. So if we look at the pressure profile, it is going to decrease until it reaches the pressure, until this reaches the sonic velocity. Past that, it cannot decrease. Until it gets out here, out in the open, and right now we have an expansion. But from here to here, which is what we're looking at, the pressure here is called the choke pressure. So if this happens, now, right, if our tank wall is only this thick, then, so that we don't reach the choke velocity, then this is going to expand down to our, okay, so what we have to look at is this pressure is higher than this.
What?
Okay? So this happens
What?
if the pressure cannot equilibrate to this pressure before we exit the tank.
Wait, what? Can you repeat that?
So if this pressure is very low, then we're going from a very high pressure, and it's gonna decrease until it reaches the choke pressure if this P choke is higher than this pressure. Okay, so it's coming out of here at a high velocity. That's why you sometimes, if you hear a leaking vessel, right, it sounds pretty bad. Have you ever heard a release from a liquid nitrogen cylinder, for example? Sometimes I think they set the pressure too high before it releases. But we have to look at what the choke pressure is, okay, for these conditions. And it turns out that this choke pressure is determined by the heat capacity ratio. So P choke is equal to our P, which is our P naught, times 2 of the heat capacity ratio plus gamma minus 1. Okay, the heat, this is the heat capacity ratio, it's Cp over Cv. That you should have heard of already from thermal. Okay, but basically in a problem like this, what you want to do is you want to take that pressure in the tank and calculate what your choke pressure would be under these conditions. If P choked is higher than P atmospheric, then you're going to have choke conditions. Vice versa, if P atmospheric is lower than this, then you're going to have choke. And what that means is that you're going to limit your mass flow rate out of that hole, right? Because we're limited by that. And it turns out if you look at, there is a table in the book, we're going to look at that, so that gives you the heat capacity ratio for specific gases. If you don't have the heat capacity ratio for a gas that you're looking at, you can't approximate it with these. So for a monatomic gas, the heat capacity ratio is about 1.67.
Is this in the book?
1.4. This table is in the book too.
Do you know what table it is? Just so I can find it.
No, I don't think the table 4.3 is the one with the actual numbers on it. So I'm actually not even sure that this is considered a table in the book, but it's given there. So if my guess, if it has a table number, is 4.4-2 or 4-3. Okay, but 4-4. 4-3 is the actual numbers for specific gases. So there's a limited amount that you have. But for triatomic gas, it's 1.32. And what you'll see is that the choke pressure is about half, give or take a few, right? 0.48, 0.5, half of this pressure. Okay, so you can imagine that any cylinder gas cylinder you're going to have in your lab is going to have a little higher pressure than whatever 32, right? So the likelihood of, if you have a leak that you have, it's very high that you will have choke flow out of that hole. Okay, so we have to separate two cases here when we're dealing with flow of vapors and gases through a hole. We have the non-choke conditions and the choke ones. But we still have to solve this equation, right? And for a compressible fluid, density is a function of pressure, and what we'll do, not sure how familiar you are with this, but what we can do, I don't know if you saw this equation in thermal, it might depend on who was teaching you thermo. But this is the equation for an adiabatic compression for an ideal gas. Right? So again, what we're limiting ourselves to is an ideal gas. Right? But what you can see, if we can, so in the equation when we need to solve the P over rho, right, we can use the fact that P is equal to P naught or really what we need, right, is that's just not the capacity ratio, that's the density. So we're going to use that density is equal to the density, whatever zero conditions we have, times P over P naught, 1 over the capacity ratio. Okay, so we put that into our mechanical energy balance. We solve that for this, and with delta Z equals 0, and doing what we did for, if you remember, we said that the friction factor is proportional to the pressure drop. Okay. This is not a derivation that I expect you to do, right? But if you do it, that's what you will end up with. Okay, so you recognize, and at least now you know where the P over P naught, the 1 over gamma, comes from. Right? It's just we integrated this part here with this from P naught to P. Okay, that's not a derivation that you need to know. You need to know when to use this equation. Okay, so this is only for when our velocity coming out of here is not choked. Okay, so in other words, your P out here is larger than P choke. Yes?
Is that equation, like, did you plug in for the friction factor at?
So the frictional factor, right, you have our friction here is in our C naught again, right? So, you know what I didn't do, I just realized last time, is show you where C naught, the number 0.61 actually comes from. It's if you put in, right, we have our Kf, or our friction factor is equal to the sum of Kf, right? If you just use Reynolds number, wait a minute, it's 160, right? Over the Reynolds number plus 0.5, that's the entrance, and then plus 1.0, and you solve for this, your friction factor, or right, the multiplication there is actually 0.63. So in other words, you can look at that as if you just have an entrance and an exit term. Did that answer your question? Okay, so now if we have choke pressure, okay, so our P2, which is no longer our atmospheric pressure, right? Even though we have atmospheric pressure on this side, but up here, our P2 now is equal to P choke. Right? We have the sonic velocity, which means this is fixed, and our QM is only dependent on the heat capacity ratio, right? The heat capacity ratio in this form. And of course the conditions that we have. Okay, so it is dependent on the pressure in here, right, and the temperature. But under these conditions, you have to use that C naught is equal to 1. It's like it doesn't really matter. The enters and exit terms are not going to slow down, right, that velocity out of there at all. Coming out there very fast.